Let me share the screen with you. You can see my screen, right? Yes.
Yes, sir.
Okay, okay. So here is first problem for today. That is, consider classical harmonic oscillators. So it's consider that there are n harmonic oscillators with coordinates and momentum given by Qi and Pi. So Qi are the coordinates of the ith oscillator and Pi is the momentum of the ith oscillator. And the energy of the ith oscillator is given by this Hamiltonian. Okay, so the total energy, the Hamiltonian of the full system is given by summation over I going from 1 to capital N, Pi square by 2m plus m omega square Qi square by 2, where omega is the natural frequency of each oscillator. And these oscillators are independent. That is, they are not coupled to each other. So the first question is that calculate the entropy as a function of the total energy. So, do you remember how to calculate this entropy and as a function of total energy? Yes. Do you know how to calculate entropy when I'm giving a Hamiltonian of the system? So, if you would recall, when we had learnt about entropy in our initial lessons, so what we had done was that we had calculated the number of microstate corresponding to a given macrostate, right? So that was the entropy of that macrostate. Okay, and once we so basically we have to count the number of microstates in the macrostate, and then the entropy turns out to be the logarithm of that quantity, right? So how do we calculate the number of microstates or a Hamiltonian like this? So when we had the ideal gas, then this potential energy term was not there. It was only the kinetic energy of free particles, right? And then we had calculated the volume, the 6n-dimensional volume of phase space which the ideal gas occupies, right? So if I have the ideal gas in a box of length volume L cube, then the position of the particle could be anywhere within that box, and the momentum can have any value in the momentum space, right? In that way we had defined this 6n-dimensional phase space, and from that 6n-dimensional phase space we had calculated the number of microstates corresponding to a given macrostate as the total volume enclosed within the 6n-dimensional phase space corresponding to that macrostate, which was defined by the Hamiltonian, right? So we do the same thing over here, but the difference is that here there is an extra potential energy term. So we need to make some modifications to our calculations. So how do we do that? So the volume of accessible phase space for a given total energy is proportional to this quantity, right? So this is an integral over the position coordinates and an integral over the momentum coordinates. So there are n position and n momentum coordinates. So it's a 2n dimensional phase space. Okay. So dn dimensional, where d is the dimensionality of the box. Now, this is the energy Hamiltonian which is given to me. Then, what is the surface of constant energy in 2n dimensions? Why? Because when I did not have this thing, then the surface of constant energy was a sphere, right? So all the energy states which were on the surface of the sphere corresponded to a given macro state, right? But in this case, the surface of constant energy is no longer a sphere, but an ellipsoid. Okay, why an ellipsoid? Because this equation is of the form of an equation of an ellipse. If I consider only one oscillator, then this is like pi square by 2m plus m omega qi square by 2 equal to E. So you can see this is an ellipse in the phase space which is spanned by pi and qi. So if there are n number of such axes, then it becomes a 2n dimensional phase space which is spanned by an ellipsoid. So how do we go from an ellipsoid to a sphere? Because sir, calculating the surface area of an ellipsoid is a difficult task. So what we do is that we do a canonical transformation. That means we transform the coordinates of the ellipsoid such that we get a sphere in terms of the new coordinates. And what are the new coordinates that we have? The new coordinates are qi dashed and pi dashed, where qi dashed is equal to square root of m omega qi and pi dashed is equal to pi by square root of m omega. So if I now write this Hamiltonian in terms of these new coordinates, then the Hamiltonian becomes equal to omega by 2 summation I equal to 1 to n pi square pi dash square plus qi dash square. So you see that in the phase space which is spanned by the pi dashed and qi dashed, this Hamiltonian actually represents a sphere in 2n dimensions instead of an ellipse. Right, so this is how it makes our calculation easier. So what happens is that we now calculate the surface area of the sphere in the space spanned by pi dashed and qi dashed, which is given by this integral over here. And we know that the radius of a hypersphere, of the hypersphere which is defined by these vectors, it is equal to square root of 2e by omega, right? This comes from this equation. So, since the volume of the d-dimensional sphere of radius r is given by st r to the power by d, r to the power d by d, we obtain this expression for the volume integral. So, the entire volume of phase space in the 2n dimensions gives us the total number of possible microstate corresponding to that given macrostate. So, therefore, this basically becomes if you replace s here, st is the solid angle in d dimensions. If I use the expression for that and then I multiply with r to the power d by d, then I obtain this integral. Here, small d is equal to 2n, okay, because the 2 capital N, because the dimensionality of the phase space is 2n. And so this is the total number of microstates corresponding to a given macrostate. And therefore, the entropy is given by the log of this quantity. Therefore, S is equal to Kb log omega, which is nkb log 2 pi small e capital E by capital N h omega. Right. So this is the entropy of the system. And as you can see, the entropy is an extensive quantity. Okay. So any doubt in this calculation or any question? Okay.
No
So,
doubt, sir.
okay. So the next question is that you have to calculate the energy and his heat capacity as functions of temperature and capital N. So what is the expression for temperature? So from the expression of temperature, you know that in thermodynamics, temperature is defined by 1 by T equal to del S by del E, where E is the internal energy of the system at a constant N. So you have this expression for S over here. If I do del S by del E, then what happens is that 1 by T is equal to N kb by E. All right, so E is equal to nkBT. So this is the expression for the internal energy, and therefore the heat capacity, which is C, is basically dE by dt. That's why it is equal to nkB. Okay, and the next question is that find the joint probability density for a single oscillator. Hence, calculate the mean kinetic energy and mean potential energy for each oscillator. So we have to first find the joint probability density for a given oscillator. So what is the probability of an oscillator to have momentum P1 and position Q1? So the probability of having momentum P1 and position Q1 is given by this expression, right? And in order to find this, I basically integrate the Hamiltonian over all the coordinates other than P1 and Q1 and then divide by the integration over all coordinates including P1 and Q1, right? So this can be then written in terms of this quantity where omega of n minus 1 en minus 1 denotes the total number of microstates that can be formed with n minus 1 oscillators having energy en minus 1, where en minus 1 is basically the total energy minus the energy of the oscillator denoted by p1 and q1. Okay, so this is E minus p1 square by 2m minus m omega square q1 square by 2. And then I divide this expression by h into omega ne. Okay, So if I do this and I use the expression for omega, which I had obtained earlier over here, that was omega equal to 2 pi e by h omega whole to the power n by 1 by n factorial. If I replace this over here and here, then I get this expression for the probability. Now, since we are working in the thermodynamic limit, so we take n being very large. Therefore, n minus 1 is almost equal to n. If we do this, then we could basically replace the n minus 1 over here by n, and we set E equal to nkt, which we had obtained earlier. Then once we do that, we can get an expression like this. So you see, basically this is 1 minus this quantity over here. This is a very small quantity because n is large. So if I think of the Taylor series expansion for e to the power a minus x, so e to the power minus x is basically 1 minus x when x is very small. So if I consider this to be my x, then I can write this quantity as e to the power of minus x, right? To the into n, because I have n over here at the top. So therefore, this is the expression of the probability. That is the probability to find an oscillator having momentum p and position q. So you see, it is a normalized product of two Gaussians. So this is one Gaussian in respect to momentum coordinates, and this is another Gaussian with respect to position coordinates. Now then, the mean kinetic energy will be given by expectation of p square by 2m, which is basically integral of p square by 2m into this probability multiplied over dq and dp. And so this basically this decomposes into a product of two Gaussian integrals, which one can easily do, and one finds this is equal to kBt by 2. And an interesting result is that the mean potential energy, which is the mean of m omega square q square by 2, this also turns out to be equal to kBt by 2. So you see the kinetic energy and the potential energy are equal at thermal equilibrium. And this is nothing but an expression of equipartition of energy, which states that in thermal equilibrium, every degree of freedom will have the same amount of energy. Right. Okay. So that solves the first problem, which was of classical harmonic oscillators. Now we move on to quantum harmonic oscillators. All right. So here, instead of the classical one, we have n independent quantum oscillators, which is subject to a Hamiltonian of this form, where Hamiltonian is equal to summation I going from 1 to n h cross omega ni plus half, where n is the quantum occupation number for the ith oscillator. Here also you have to find the entropy as a function of total energy. Now, one thing to note over here is that quantum systems are discrete system. Unlike the previous one, that was a classical system. This is a discrete system, right? So you can't integrate over a volume of phase space. On the other hand, what you have to do is that you have to individually count the number of discrete microstates which correspond to a given macro state. Therefore, the total number of microstate can be regarded as a number of way of rearranging m balls and n minus 1 partitions along a line, where m is equal to the total number of balls which are there. Now, here by balls, I am representing one particle. Okay, so a given particle can be on any energy level, and there are capital N number of energy levels. So this basically becomes a problem of how I can arrange the total number of particles into different energy levels. Basically, I have to arrange the m particles into n energy levels. That is like arranging m balls into and n minus 1 partitions along a one-dimensional line. So what are the possible ways of arranging m balls into n minus 1 partitions along a given line? That number of possible arrangements is given by omega, which is this. So the total number of ways in which you can arrange m and n minus 1 quantities is m plus n minus 1 factorial ways. And then you divide that by m factorial and n minus 1 factorial, which are the number of similar permutations among the individual objects themselves, right? So this is basically m plus n minus 1 c m, right? That is what this quantity is basically m plus n minus 1 c m, number of possible combinations. So this is the total number of microstates. And if I take the log of that quantity, then I get the entropy, which is equal to kb log omega. All right, so the entropy turns out to be equal to this quantity. So then what is the next question? The next question is that I have to calculate the energy and the heat capacity as functions of temperature T and the number of particles N, similar to what I had done earlier. So now you know that temperature 1 by T can be written as del S by del E at a given N. So if I do del S by del E of this expression over here, then I obtain this is equal to Kb by H cross omega m plus n minus 1 by m. Okay, where m is where I basically have to replace m by this quantity over here because m is the summation over ni. So m is equal to E by H cross omega minus n by 2. So the E dependence is only there in the m. So if I do del S by del E, it is nothing but 1 by H cross del S by del E. Del S 1 by H cross del S by del M. And if I do del S by del M of this quantity, I arrive at this expression. Okay, so I substitute for, I substitute the expression of M which I had obtained over here. This M I put over here. All right, so this becomes E plus H cross omega, E by H cross omega plus n by 2 minus 1, and this becomes E by H cross omega minus n by 2. Then I go to the large n limit and I neglect the 1 over here. So this is what this quantity finally becomes. Right. So this is equal to 1 by T. Now if I invert the expression, that is I take this quantity is basically then becomes e to the power of H cross by kBT. Okay. Exponential H cross by kBT, and I finally get my energy by inverting this expression. So this is the expression for the energy of the system of n quantum harmonic oscillators. And the heat capacity follows if I do del E by del T of this expression, and this is the expression for the heat capacity which I get. All right. Now find the probability that a particular oscillator is in the nth quantum level. So to do this, we carry out the calculations as we had done earlier. That is, we first sum over all the other n minus 1 energy levels and assume that the nth energy level does not have a single particle. That means it lacks one particle. So therefore, the total number of microstates is that of the n minus 1 particles having energy given by E minus n plus half h cross omega divided by the total number of microstates of the original system. This will give me P small n. So if I now do this calculation, then and I simplify the expression by considering the large n limit, then this turns out to be n into m plus n raised to the power minus n minus 1 into m to the power n, where basically I have used the approximation for large n. That is, if in case of I have n, then n minus 1 I have taken as n while deriving this expression. Okay. So therefore, if I further simplify this expression, then what I get is that Pn turns out to be of this particular form. So if I use this uh, for Pn, then now if I use the expression for temperature, which I had obtained earlier, then I know that this quantity is equal to e to the power minus n h cross omega by kBt, right? Basically, I take h cross omega by kBt over here and I exponentiate and then take it to the power n. Therefore, this is equal to e to the power minus n h cross omega by kBt. So if I substitute this quantity back over here in this expression, then Pn becomes equal to e to the power minus n h cross omega by kBt into 1 minus e to the power minus h cross omega by kBt. Okay. So this is the expression for the probability of finding an oscillator in the small nth quantum level. Now the next question is comment on the difference between the heat capacities for the classical and quantum oscillators. So previously, what was the heat capacity which we had obtained for the classical oscillator? It was n kb, right? Over here. Now, if I do del E del T, then the heat capacity which I obtain is n kb multiplied by this quantity h cross omega by kBt whole square into e to the power this thing by e to the power this thing. So this is the heat capacity of the quantum oscillator, right? So now if I go to the high temperature limit, that is h cross omega by kBt much less than 1, and then I use the Taylor series expansion for the exponential, then you see that this quantity is basically 1 plus h cross omega by kBt, which I can take as 1. And if I put 1 plus h cross by kBt in place of this quantity, then I get an h cross omega by kBt whole square in the denominator, which cancels out with this person over here. And finally, I get the quantum heat capacity is equal to nkb, which is the classical one. So you see, like we had studied for the case of quantum ideal gases here also, if I take the high temperature limit, then the system of quantum harmonic oscillators approaches the classical one. So at low temperatures, the quantized nature of the energy levels of the quantum oscillators becomes noticeable. In the limit of temperature going to zero, there is an energy gap between the ground state and the first excited state. This results in a heat capacity that goes to zero exponentially. So let's see what happens when T goes to zero. So when T goes to zero, then the limit h cross omega by kBt is much greater than 1, right? So then the quantum heat capacity can be written as nkb h cross omega by kBt whole square into e to the power of minus h cross omega by kBt. Why? Because this quantity is basically e to the power h cross omega by kBt whole square. That cancels out one factor from the top, and I get e to the power of minus h cross omega by kBt. So you see, in the t going to limit zero limit, the quantum heat capacity falls off exponentially fast. Right, and this is because there is a gap between the energy of the ground state and the first excited state. Okay, so that solves the problem of a harmonic oscillator. So is there any question or doubt from this? Any place you want to repeat again or any questions? See if there are questions in the chat. Okay, so if there is no question, then I will move on to the next question, which is about relativistic particles. In So let us say that there are capital N number of indistinguishable relativistic particles which move in one dimension, and it is subject to a Hamiltonian. So you see, all particles are moving in a given direction and it is subject to the Hamiltonian given by this. So the energy of, you know that the energy of a relativistic particle is can be written using Einstein formula is equal to mc square, or in other words, it is equal to p into c, where c is the speed of light and p is the energy of momentum of the particle. So I have my particles moving in one dimension, and the potential energy is equal to 0 for 0 less than qi less than L, and it is equal to infinity otherwise. So what this means is that I have the I have the relativistic particles moving along a one-dimensional space, and the one-dimensional space is bounded at its two ends. One is at 0 and one is at capital L. So my particle will always be contained within this limit 0 to L. Okay. So now consider a microcanonical ensemble of the total energy E. Now compute the contribution of coordinates qi to the available volume in the phase space. So you know that the total volume in the phase space has two contributions. One is from the coordinates and the other is from the momentum that we had seen earlier. So first question is the contribution of the coordinates to the phase space, and second time we have to calculate the contribution of momentum. So you know that there are n number of coordinates because there are n particles over here. So there are n number of position coordinates, and the total amount of space which they are restricted to has a length of L, right? So there can be L to the power of n number of different contributions from these n number of coordinates, and in order to avoid overcounting, that is, since the particles are indistinguishable, we have to divide by the total number of permutations of these particles. So we have to divide by n factorial. So therefore, the total contribution to the overall number of microstates, which comes from the position coordinates, is equal to L to the power n by n factorial. Now you have to calculate the contribution of the momentum coordinates to the total number of microstates. So the momentum coordinates satisfy this particular constraint. Okay, this comes from this Hamiltonian over here only. So the momentum coordinates satisfy the constraint that summation I equal to 1 to capital N pi is equal to E by C. Okay, so initially when we had pi square by 2m, so we saw that it was the surface of a sphere, right? It was a sphere in 3D or an ellipsoid in 3D and all sorts of things. So in those cases, that was how the constraint was defined. That was the geometric structure these constraints represented in the phase space. Okay, so when we had a sphere, so we had to calculate the volume which of the space which was which was contained inside the sphere in a certain number of dimensions. That gave me the total number of microstates that the system can contain. Okay, so what does this type of constant over here represent, right? So if I take two particles, for example, then P1 plus P2 is equal to E by C, right? So the P1 plus P2 can be seen as the length of, so if you consider P1 to be the length of one side of a triangle and P2 to be the length of another side of a triangle, then you see that P1 plus P2 equal to a constant value says that the perimeter of the triangle has to be a constant value, right? Because the perimeter is the sum of the three sides, and if I define the length of two sides uniquely, then the third side of the triangle is also uniquely defined, right? So if I take two particles, then I'm working in two dimensions. So then this constraint represents a triangle. And if I'm working in three dimensions, then there are three particles. So P1 plus P2 plus P3 is equal to some constant. So that represents a tetrahedron. So similarly, if I'm working in n dimensions, then P1 plus P2 plus P3 plus up to Pn equal to some constant. This represents the surface of a hyperpyramid in n dimensions. Okay. So yeah, so basically a tetrahedron is a pyramid. So this represents a hyperpyramid in n dimensions or an n-dimensional tetrahedron. Okay, it's a polyhedra. So if we ignore the difference between the surface area and the volume in the large n limit, then we have to basically find the volume contained within the n-dimensional hyperpyramid. And what is the volume of the hyperpyramid? The volume of the hyperpyramid in d dimensions is given by r to the power d by d factorial, where the hyperpyramid is defined by this constraint. So in this case, my r is equal to E by C. Right. Therefore, the contribution from the all the momentum is given by 2 to the power n into 1 by n factorial E by C raised to the power n, because I'm looking in an n-dimensional space. And why does this factor of 2 to the power n come over here? This is because my momentum can have both negative and positive signs. And if you look at this expression over here, this constraint contains a modulus, right? So it tells me about both positive and negative signs. So in order to take that into account, I have to multiply by a factor of 2 to the power n. So this is the contribution from the momentum coordinates to my total number of microstates. Okay. So then basically the total number of microstates that the system contains. So this is a volume. Okay, but what we are concerned is with the surface, because as I had mentioned, if it was a triangle, we would have to be we would have to take the perimeter, because anywhere inside the perimeter, inside the volume of the triangle, it is inaccessible by these coordinates, because they won't satisfy the constraint that P1 plus P2 equal to some constant, right? So we have to only consider those states which live along the perimeter of the triangle. Therefore, here also we have to consider those states which live along the surface area of the d-dimensional hyperpyramid. And the surface area is given by square root d r to the power d minus 1 by d minus 1 factorial. Therefore, the total amount of accessible energy space is given by 2 to the power n into square root of n by n minus 1 factorial e by c raised to the power n minus 1 into delta E by C, where delta E by C represents a small shell of thickness of delta E about the surface of this hyperpyramid. Okay, so all those states which are along the surface of this hyperpyramid within a thickness delta E of it are within are contained are counted within my total number of microstates. So if I multiply the two of them, that is, if I multiply this contribution and this contribution which comes from the positions, then I can get the total number of microstates, which is precisely what my next question asked me to find out. So I have to find out the entropy of the system. So in order to calculate the entropy, I have to calculate the total number of microstates, which is basically 1 by h to the power n, ln by n factorial into this quantity over here. So if I ignore the subleading terms in the limit of large n, and if I take the logarithm of this quantity, I can get the entropy S, which is given by this particular formula. Okay. Now you have to calculate the pressure. So what is pressure? Pressure comes from the first law of thermodynamics. Okay, so dE is equal to TdS minus PdV plus mu dm. From this, I get P is equal to uh, T into del S, T del S del L, right? So basically, I put set dE equal to 0, and this dn is also equal to 0 because we are working in the microcanonical ensemble. Here E and N are constants, right? So therefore PdV is equal to TdS. Therefore P is equal to 1 by T. Sorry, P is equal to T into del S by del V. And here del V is basically del L. Therefore P is equal to T into del S by del L at a constant T and N. So if I do del S by del L of this expression, then I get P is equal to NKT by L. So this basically looks like the ideal gas equation of state where L is the volume. So P is equal to NKVT by the volume. Okay. Now we have to obtain the heat capacities CL and CP. That is the heat capacity at constant volume, which is constant length L and constant pressure P. So the heat capacity, since I have, so the calculating the heat capacity is a straightforward thing because I have to basically do del E by del T. So I know that 1 by T is equal to del S by del E at a given volume and N. So from this, I obtain E is equal to NKT. And if I do del E by del T, I get CL is equal to NKV. Now we have to include the work done against the external pressure. And if I use the equation of state, then Cp is equal to del E by del T at constant pressure and N plus P into del L del T at constant pressure and N. Okay, so I get this from the equation of state basically. And del L by del T into P again gives me NKV, and therefore this becomes equal to 2 NKV. Okay. So what is the probability of finding a particle with momentum P1? So we fix a momentum of a given particle as P1 and allow the rest n minus 1 particles to share the rest of the energy, which is E minus Cp1. Right. So then this becomes equal to the total number of microstates which is obtained by the which are there in the new system. That is system of n minus 1 particles with energy E minus Cp1 divided by the total number of microstates that were there in the original system. Right. And since we are not interested in the position coordinates, we can get the probability from the ratio of the phase spaces from the momenta itself, right? Because we are only fixing the position of the we are only fixing the momentum of the particle and not the position. Therefore the position coordinates, they cancel out from the numerator and denominator, and simply we can obtain the probability from the number of microstates of the momentum. So that is the from the momentum contribution to the total number of microstates. So if I evaluate omega p for this and omega p for this, and if I simplify further in the large n limit, then I obtain that the probability of a particle containing a momentum p1 is equal to Cn by 2e e to the power minus Cn by Cn p1 by e. Okay, so as you can see, it follows a sort of a Boltzmann distribution as a function of temperature. It follows an exponentially falling of this exponential distribution over here. And if I put E equal to n kBt, then I obtain that the probability is equal to C by 2 kBt exponential of minus Cp1 by kBt. So at a given temperature, the probability of having a particle with momentum P1 has an exponential distribution. Okay, so any question up till now or any doubts? Okay, so if there are no doubts, then I'll move on to the next question. That is a hard sphere gas. So consider so suppose I have a gas of n number of hard spheres in a box. So what do I mean by a hard sphere? So for ideal gases, we had neglected the volume of the molecules, right? We had taken the molecules to be point particles. So here in a hard sphere gas, the molecules have a finite radius. The particles of a gas have a finite radius. Okay. And the the gas basically excludes the volume of the particles. So if you have n number of particles within a box of volume V, then the total volume occupied by the gas will be the volume of the box minus the volume occupied by the particles themselves. Okay, so that is what this question basically says, that a single sphere excludes a volume omega around it, while its center of mass can explore the entire volume of the box if the box is otherwise empty. So basically, the volume of this particle is very small, but it's not negligible. Okay. And there are no other interactions between the spheres except for the constraints of hardcore exclusion. That means the centers of spheres cannot overlap with each other. That means if the spheres collide, they cannot coalesce into each other. They will collide and then they will move away from each other. Okay. So their volumes cannot be deformed. They can stick to each other if they want. So now you have to calculate the entropy as a function of total energy. So the available phase space volume for n identical hard particles is given by 1 by n factorial h to the power 3n into the integral over the surface of over the constant energy volume over the position coordinates and the momentum coordinates. Right. So since there is no interacting potential over here, the energy is basically the free energy of each particle. That is, total energy is equal to summation I equal to 1 to capital N pi square by 2m. Again, so this is an n-dimensional hypersphere in the momentum space. And we know the volume and the surface area of the n-dimensional hypersphere in momentum space. And so this is what it turns out to be. So omega is equal to 1 by n factorial h to the power 3n multiplied by the volume of an n-dimensional hypersphere having a radius of 2 me into the integral over the position coordinates. Now, how do we do this integral over position coordinates? Earlier, we had saw that it was basically capital V raised to the power of n, but here it is not so. Why? Because the joint integral over the spatial coordinates will exclude the volume which is occupied by individual particles, right? So how do we do this integral? We do this integral one by one. So first we integrate over q1, then we integrate over q2 and so on. So let us suppose we integrate over q1 first. That means the q1 particle can exploit the entire volume of the box, that is phi. That's done. So now I integrate over the second particle. So the second particle will explode only the volume of the total box minus the volume of the first particle, right? So it will explode a volume given by V minus omega. Similarly, the volume available to the third particle will be the total volume minus the volume of first particle minus the volume of second particle. So V minus 2 omega and so on and so forth. So therefore, this volume integral ends up becoming something like this. So this is equal to V into V minus omega by into V minus 2 omega dot 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 up to V minus n minus 1 omega. Now we can use this expression in the large n limit, that is V minus a omega into V minus n minus a omega is equal to V minus n omega by 2 whole square. So if I use this approximation, then this integral turns out to be nothing but V minus n omega by 2 whole to the power of n. Right. This easily follows from this expression. So therefore, the total number of microstates is this quantity multiplied by V minus n omega by 2 whole to the power n. And therefore, the entropy of the system is kb log of omega, which is equal to this. Okay. So this is how I calculate the available volume of the available phase space for a hard sphere gas, which contains n number of hard sphere in a box. Now the next question is I have to find the equation of state of this gas. Okay, so the equation of state I can obtain from the first law of thermodynamics. That is PdV is equal to SdT, because I'm again working in the microcanonical ensemble where E is a constant. Therefore, P by T is equal to del S by del V at a constant E and N. So if I do del S by del V, this becomes equal to NkV by V minus N omega. Therefore, the equation of state is equal to P into V minus N omega by 2 is equal to NkVT. Right. So here is the volume correction which comes out because of the volume of the hard spheres, right? So if I had considered this to be an ideal gas, then omega would be 0 and I will get the ideal gas equation of state, that is PV equal to NKT. Similarly, one can also calculate the isothermal compressibility, which is given by this expression 1 by V minus 1 by V del V by del P at constant T. So the isothermal compressibility is this thing. So since I know P in terms of V, I can simply invert the equation of state and calculate the isothermal compressibility from here. And this turns out to be equal to N kBT by P square V, which is always greater than 0. And it is explicitly all greater than 0 because all these quantities are positive. And this is required for stability constraints. Okay. So that solves the question about hard spheres in a box. So the next system that we will look into is a non-harmonic gas. So earlier we had seen what a harmonic gas looks like, a harmonic gas kept in a harmonic potential. So that had a form of like P square by 2m plus m omega square q square by 2. Here we look at a non-harmonic gas. So it's like a general ideal gas. And we look at this using statistical mechanics instead of kinetic theory. Okay. So basically, when we look at statistical mechanics, we calculate the partition function and other quantities of interest. Okay. So consider a gas of n non-interacting atoms in a d-dimensional box of volume V having a kinetic energy which is given by summation I equal to 1 to capital N A into Pi to the power of S, where Pi is the momentum of the ith particle. So first you have to calculate the classical partition function at temperature T. So what is the partition function? So partition function is basically integral over this quantity e to the power of minus beta of into the Hamiltonian e to the power minus beta h, and h was given by this quantity over here, right? So the partition function and is basically 1 by n to the power 1 by n factorial in order to account for the indistinguishability into h to the power of dn, because I'm working in a d-dimensional space of n particles, into the integrals over all position and all momenta e to the power of minus beta summation I equal to 1 to n a into pi to the power of s. Okay, so this is the expression for, and basically this simplifies to the product of these two integrals raised to the power of n. Why? Because all the individual momentum coordinates have the same momentum, have the same particular form, right? So this is basically this product of two integrals raised to the power of n. Now, if I ignore the hardcore exclusion, because I'm considering only point particles over here, so there is no the hardcore exclusion of spheres. So therefore, each atom can occupy the entire of the d-dimensional volume V. Therefore, I have the integral over d dq becomes equal to V, and therefore I have factor of V to the power n coming out of the integral. And then I have an integral over ddp e to the power of minus beta a p to the power s, and the product of n number of such integrals. Okay. Now we know that the d-dimension we use the spherical symmetry. That means we consider that all possible values of momentum are equally achievable within the sphere of radius in the momentum space, which is equal to p. Right. Therefore, the d-dimensional integral over p becomes equal to st into dp into p to the power d minus 1, where st is the surface area of a unit sphere in d dimensions. Okay, so basically st is the solid angle in d dimensions. Therefore, the partition function is become equal to v to the power n by n factorial h to the power dn into st into integral from 0 to infinity dp p to the power d minus 1 into exponential of minus beta a p to the power s. And then there is a product over n number of these integrals. Now we make the substitution that x is equal to beta a to the power 1 by s into p. And why do we do this? If I make this substitution, then I get this integral in terms of a product of n number of gamma integrals, right? So gamma integral, here you can see that this is basically a gamma integral of the form of gamma d by s, right? And therefore this can be written in terms of this expression over here, where c d comma s is basically 1 by s comma d by s, right? Therefore the partition function finally ends up becoming 1 by n factorial v st by h to the power d into s whole to the power n a by kbt whole to the power of minus dn by s into gamma of d by s whole to the power n. So this is the expression for the particle partition function for a non-harmonic gas. Okay, so once we obtain the particle partition function, we have to calculate the pressure and the internal energy of this gas. And an interesting thing to note is that how the equipartition theorem gets modified for non-quadratic degrees of freedom. So what is the pressure? The pressure can be obtained from the Helmholtz free energy. So Helmholtz free energy is basically E minus Ts, which is equal to minus kBT ln Z. Okay, and P is equal to minus del F by del V. So this is equal to minus kBT into del ln Z by del V. And minus minus becomes plus. So this is kBT into del ln Z by del V. And if I do log of this quantity and then do a del V of that, then I get P is equal to NkVT by V. And the internal energy is equal to minus of del ln Z by del beta at a constant V. Okay. So basically this is equal to D by S NkVT. So for each degree of freedom with energy A into Pi to the power S, we have the average value of energy to be equal to D by S kBT. This is total energy. So each degree of freedom has an energy d by s kBT. So if it was a three-dimensional ideal gas, then it would be 3 by 2 kBT. And so basically the amount of energy that goes into each degree of freedom, it depends on these two factors. One is the d, that is the dimension of the space I'm working in, and the other is the s, which is the power of the momentum in the energy equation. Now you consider a gas of n molecules, each having energy given by Hi, which is equal to A into mod Pi1 to the power s plus Pi2 to the power s plus K into Qi1 minus Qi2 raised to the power of T. Okay, so Pi1 and 2 basically represent the two kinds of molecules. So since I'm considering a diatomic gas of n molecules, therefore 1 and 2 basically represents to the two atoms within a given molecule. So here what we have to do is that we have to calculate the expectation value of the potential energy, that is Qi1 minus Qi2 raised to the power T at a constant temperature. So here is the Hamiltonian which I had. So the expectation value of this quantity is basically 1 by n factorial into product over all the position and momentum coordinates into this quantity, that is Qi1 minus Qi2 to the power T into e to the power of minus beta h, right? Divided by the 1 by n factorial integral over the product of over momentum and position coordinates e to the power minus beta h. Now, how do I evaluate this complex looking integral? What I do is that I consider two variables. I change variables to q1 minus q2 and q1 plus q2. So I use one kind, I denote x as q1 minus q2 and y as q1 plus q2 by 2. Actually, this should be a q1 minus q2 by 2 for x as well. Okay. So then q1 becomes equal to x plus y and q2 is basically x minus y, right? Then the Jacobian of this transformation, then if I transform the variables to this new coordinates, then I basically get the left hand side to be equal to an integral over x and y, x to the power t e to the power of minus beta k x to the power t. Okay, because Hamiltonian basically becomes, this thing becomes equal to kx to the power t. And I ignored the uh, integral over the momentum coordinates because I'm only concerned with the integral of position coordinates, right? Because so that is why what happens is that the integral over the momentum coordinates, they cancel out from the numerator and denominator. That's why I have neglected those. And the denominator similarly becomes equal to ddx ddy integral e to the power of minus beta x to the beta k x to the power t. Okay. So again, the y integral goes up because this this quantity only depends upon x over here, right? So if I simplify this expression further and I do the d-dimensional integral over x by introducing this variable z equal to beta k to the power 1 by t into x, then what I obtain is that the expectation is equal to d by t into kbt by k. Okay. So there is also another alternate way of doing this. So basically, this is the quantity over here. Therefore, right. So K, this quantity is basically become equal to K into XT expectation. So this is equal to this quantity. Therefore, this follows. So another way of calculating the expectation volume value of this quantity is if I look at the partition function over here, that is, where did the Z go? Yes. So if I take a look at the partition function, then I can simply take the, because the form of the partition function is given over here as a sum e to the power of minus beta h. Okay. So h is equal to a into pi1 plus pi2 plus k into qi1 minus qi2. Right. So if I take the log of the derivative of the log of the partition function with respect to beta k, then this quantity directly follows from that. And you see that this will also yield the same expression with a factor of n over here because I'm summing over I equal to 1 to capital N. Okay, so this is nd by t into kbt by k. Okay, so the next question is that I have to find the ratio of the heat capacity, that is Cp by Cv, for this diatomic gas. So for the ideal gas, we know that the Cv is basically given by dq by dt at constant V, which is equal to dE plus PD by dt, which is equal to d by dt. And Cp is equal to dq by dt at constant P, which is equal to d by dt at constant P plus P into del V by del T at constant P. Right. So since PV is equal to NKBT for an ideal gas, Cp is equal to dE by dt plus NKB. Okay. So now what we do is that this is all for an ideal gas. So how do we do Cp by calculate Cp and Cv for this this type of gas? So we look at the partition function for that. So the partition function for this diatomic gas is given by 1 by n factorial h to the power dn integral over all the position and momentum coordinates e to the power of minus beta hi, which can be written in a simple form as 1 by n factorial h to the power dn into z1 to the power of n, where z1 is equal to integral over the position and momentum coordinates e to the power of minus beta into the Hamiltonian for a given particle, single particle. Okay, so this integral can be easily evaluated. So basically, you see that if you look at the momentum coordinates here, then this turns out to be the integral for the momentum coordinates of a single particle basically turns out to be a product of two integrals of this particular form, right? And the integral for the position coordinates becomes equal to this. So therefore, if I substitute in this expression, then the capital Z is proportional to v to the power n by n factorial into beta k. I basically make this substitution which I did over here, that Z is equal to beta k raised to the power 1 by t into x. So if I do this, Z is equal to beta k 1 by t into s, and if I put it over here, then basically this turns out to be a Gaussian integral, and this is another Gaussian integral, and there are two n number of these over here, and there are n number of these over here. So then Z becomes proportional to v to the power n by n factorial into beta k to the power of minus dn by t into beta a to the power of minus 2n d by s. Right. So after that, we can calculate the internal energy as a minus del ln z by del beta. So if I take the derivative of this with respect to beta, then this becomes equal to dn kbt into 1 by t plus 2 by s. This results in the heat capacities being as follows. So heat capacity at constant volume is equal to del E by del T, 60 and kV into 2 by S plus 1 by T, and Cp is equal to del E by del T plus P del V by del T. So this is equal to n kb into 2d by S plus d by T plus 1. Okay, and therefore then this becomes the ratio of the specific heat capacities. So is this part clear? Yes, any questions or comments? Okay, so if there are no doubts, then I will move on to the next question, which is on surfactant absorption. Okay, so what does this question say? A dilute solution of surfactants can be regarded as an ideal three-dimensional gas. As surfactants molecules can reduce their energy by contact with air, a fraction of surfactants would migrate to the surface where they can be treated as a two-dimensional ideal gas. So basically, surfactants are molecules which lower their energy by migrating to the surface. Okay, that is by contact with air. So if you spread some surfactants in a three-dimensional fluid, they will migrate to the surface and form a two-dimensional layer on top of the surface. Okay, so then they can be treated as a two-dimensional gas on top of a three-dimensional fluid. So considering the surfactants to be an ideal gas of classical particles of m in d dimensions moving in a uniform attractive potential of strength epsilon d, by calculating the partition function or otherwise show that the chemical potential at temperature T and particle density Nd is given by this expression. Okay, so we basically consider the surfactant molecules to have mass m in d dimensions, and they all of them have a uniform attractive potential of strength epsilon d. Right. So what does the Hamiltonian become? Hamiltonian is basically summation over I equal to 1 to Nd pi squared by 2m. This is the kinetic energy plus Nd into epsilon d, which is the potential energy of the surfactant molecules. Therefore, the partition function is 1 by Nd factorial h to the power dnd integral over the position and momentum coordinates into e to the power of minus beta h, where h is this Hamiltonian. So if you do this integral, then you will see that the integral of the over the position coordinates comes out automatically because there is no position over here, and then you get um, nd number of Gaussian integral over the momentum coordinates, which gives this factor of 1 by lambda d, where lambda is the thermal de Broglie wavelength, and you have this factor of e to the power minus beta nd epsilon d coming out of both the integrals. So this is the expression for the partition function. And once we know the partition function, we can calculate the chemical potential as del F by del N. F is the Helmholtz free energy, which is equal to minus kBT ln Z. So this is equal to minus kBT del ln ZT by del ND. From this, I obtain that mu d is equal to minus epsilon d plus kBT ln Vd by Nd into lambda d. Okay. So now if a surfactant lowers its energy by moving from the solution to the surface, then calculate the concentration of floating surfactants as a function of the solution concentration N at a given temperature T. So how do we do this? So the density of particles can be calculated from this grand canonical partition function. So what is the grand canonical partition function? It is given by this quantity, which is xi, capital Xi over here, which is equal to summation over nd equal to 0 to infinity z e to the power beta nd mu. So in the grand canonical ensemble, I remove the constants on the total number of particles being kept as constant. And this is important because I have particles migrating from the bulk of the fluid to its surface. Therefore, the number of particles in the bulk is not a constant, and the number of particles in the surface is also not a constant, but the total is a constant. So basically, nd here is the number of absorb particles in the surface. Okay, and this is not a constant, therefore I treat it in the grand canonical ensemble. So I know the expression for zd, which I had obtained over here. If I substitute this expression, then this becomes the expression for the grand canonical partition function. So the average number of particles which are absorbed on the surface is given by 1 by beta del mu ln of xi, which is equal to Vd by lambda d e to the power of beta mu minus epsilon d. So now we are interested in looking at the coexistence of the surfactants between a three-dimensional solution and its two-dimensional surface. So basically we have to substitute d equal to 2 and d equal to 3 to find the concentration within the volume and concentration on the bulk and look at them separately. And we have to take into account, so basically if I put d equal to 3 over here, then the average number of particles in the bulk of the fluid is given by V to the power d by lambda d, e to the power of beta mu minus epsilon 3. Okay, this is V3 and this is lambda to the power of 3. Right, so Vd was a d-dimensional volume. So here it becomes basically the volume of the fluid, the three-dimensional volume. So this is V3 by lambda to the power 3 e to the power beta into mu minus epsilon 3. So that is equal to N3, and similarly N2 is equal to V2, that is the area in 2D, into lambda to the power of 2 into e to the power of beta into mu minus epsilon 2. Right. So if I take the ratio N2 by N3, then I basically get a ratio of area by volume, that is A by V. And there is a factor of lambda which goes on top because of this factor of N3. And then you have, there's a factor of lambda which goes on top because of N3. And then you have e to the power of beta epsilon 3 minus epsilon 2, which is equal to epsilon 0. Okay, so this is the expression for N2 by N3. So now if N3 is the concentration of surfactants in the bulk, then N3 is equal to capital N. And then the concentration of molecules on the surface is basically N2, which is equal to expectation N2 by the area. So expectation N2 by area is basically expectation N3 into lambda by V into e to the power beta epsilon naught. And expectation of N3 by V is basically small n. So therefore N2 is equal to small n lambda e to the power of beta epsilon naught. Okay, so this gives me the concentration of molecules on the surface as a function of the concentration of the molecules in the volume and the total energy difference between the surface molecules and the volume molecules. That is the energy which is released by the molecule in going from the volume to the surface. Now, let us look at an interesting consequence of this fact. You see, gels are formed by cross-linking linear polymers. Okay, so linear polymers, if you cross-link them, then they form gels. And it has been suggested that the porous gel should be regarded as a fractal. Now, what is a fractal? This word might seem new to you. So fractals are basically objects which are self-similar at all scales. So if you have a fractal and if you zoom into the fractal, you will see the same structure. If you zoom in further, then you also will see the same pattern. You keep on zooming in up to infinity, you will get the same pattern. And objects like these are known as fractals, and they are found in they are very commonly found in different places in our surrounding environment. Okay. And the interesting thing about fractals is that they have a fractional dimension. Okay. So fractals are non-integer dimension objects. For example, if you have a fractal on a two-dimensional surface, then the fractal should have a dimension between 1 and 2. Similarly, if you have a fractal in a three-dimensional space, then for that fractal can have a dimension between 2 and 3. Okay. Or anything less than 3 for that matter. Right? So this is what a fractal is. So it has been suggested that the porous gels can be regarded as a fractal and the surfactants absorbed on its surfaces treated as a DF, gas in DF dimensional space, where DF is the dimension of that fractal. So can this assertion be tested by comparing the relative absorption of surfactants to a gel and to individual polymers before cross-linking as a function of temperature? So here we had the adsorption of the volumes of the molecules within the bulk on the surface. And now can we extend this theory to the adsorption of a surfactants to a gel? That means the adsorption of a surfactants to a fractional dimensional surface instead of a two-dimensional surface. Can that be done? Well, that can be easily done if I replace basically using this result found in this part, that is N2 is equal to N into lambda into e to the power of beta epsilon naught. We can do a similar thing by calculating the fraction of molecules within the bulk and the fractional of molecules which are distributed on the fractal surface. And if df is the dimension of the fractal surface, then from this expression, we can find the adsorbed particle density on the gel as n into lambda to the power of 3 minus df exponential of this factor, right? By doing a similar calculation. Therefore, by studying the adsorption of particles as a function of temperature, one can determine the fractal dimension of the surface of the gel. Okay, so the largest contribution comes from the differences in the energies. And if the leading part is accurately determined, there is a subleading dependence via lambda to the power of 3 minus df. And once one finds out that subleading dependence, one can calculate the fractal dimension of the shell. Okay, so that solves the problem of surface absorption of molecules. Now going on to molecular absorption. So suppose there are n number of diatomic molecules which are stuck on the metal surface of square symmetry. Okay, so there is a metal surface which has a square symmetry. Each molecule can either lie flat on the surface. So molecules are basically a three-dimensional object like that. They can either lie flat on the surface, in which case it must be aligned either along the x direction or the y direction, or it can stand up along the z direction. And there is an energy cost of epsilon, which is associated with the molecule standing up, and zero energy for molecules lying flat. So molecules standing up will have an energy epsilon, and the molecules which lie flat along the x or y directions will have zero energy. So what is the smallest value of energy the system can have? Well, I can have all the molecules lying flat on the surface. That will give me the total energy to be equal to zero. That is the smallest value of energy that the system can have. And how many microstates can be there corresponding to the smallest value of energy? So since there are n number of molecules and they can either lie flat along the x direction or the y direction, there can be 2 to the power of n number of microstates having the smallest value of energy. Right. And what is the largest value of microstate energy? The largest value of microstate energy happens when all molecules are pointing upwards. That is, the largest energy is equal to n epsilon. That is what this answer says over here. Now going to the next question. For microcanonical macrostates of energy E, calculate the number of states and the entropy S. So first you have to calculate the number of microstates corresponding to a given macrostate of energy E and n number of molecules. So since there are n number of molecules can be arranged in n capital N factorial different ways, and suppose out of these number of molecules I have nz molecules which are standing pointing upwards. So then capital E is equal to total, the energy of the system is equal to epsilon into nz. Therefore, nz is equal to E by epsilon. Okay. So therefore, the total possible number of arrangements of nz molecules out of n molecules is equal to nc nz. Right? So this is n factorial by nz factorial into n minus nz factorial. Then you have a factor of 2 to the power of n minus nz, because the rest of the n number of nz molecules can either lie along the two directions x or y. Therefore, the factor of 2 to the power of n minus nz. So this is the total number of possible configurations, total number of microstates that the system can have. And the entropy is basically a log of this quantity. So log of this quantity, which is given by the entropy of a two-level system. Basically, this is the number of microstates of a two-level system. Therefore, this is the entropy of a two-level system plus kb n minus nz into log n2. So this gives me the entropy of the system. Now, what is the heat capacity? Heat capacity is basically, for that I have to find the internal energy and I have to find the temperature, right? So the temperature dependence upon epsilon can be obtained from this expression 1 by T is equal to del S by del E. So 1 by T is given by this expression. If I invert the expression, I get E is equal to n epsilon by 2 e to the power of epsilon by kBt plus 1. If I do del T of this, I get C is equal to n kb epsilon by kBt whole squared 2 epsilon 2 e to the power of epsilon by kBt by 1 plus 2 e to the power epsilon by kBt whole squared. Right. So in the limit of t going to 0, this is basically equal to in the limit of t going to 0, e to the power of this quantity goes to infinity. So this is becomes equal to c becomes equal to n kBt epsilon by kBt whole square into e to the power of minus e epsilon by kBt. So that goes to 0 exponentially. So at t goes to 0, it scales as epsilon by kBt whole square e to the power of minus epsilon by kBt, which is written over here. This is the low temperature limit. And in the high temperature limit, this quantity becomes very small. So then I can Taylor expand this, and therefore this I write as 2, and this becomes equal to 1 plus 2 into 1 plus epsilon by kVt, right, whole square. So therefore this can be simplified as 1/4 of epsilon by kVt whole square, and therefore this falls up as 1 by T square in the high temperature limit as T goes to infinity. Okay, so what is the probability that a specific molecule is standing up? So the probability of a given molecule to stand up is the probability of a given particular molecule to have energy epsilon. So that can be obtained if I consider all the microstates of a system having energy E minus epsilon and number of particles n minus 1 divided by the total number of microstates of the original system, that is omega epsilon n. If I calculate this quantity, then the probability turns out to be 1 by 2 exponential epsilon by kBt plus 1. And what is the largest possible value of the internal energy at any positive temperature? So here is what I had got for the internal energy. And at any positive temperature, what is the largest value of E? So you will see that the largest value of E is achieved as T goes to infinity. Why? Because as T goes to infinity, this denominator becomes smaller and smaller, and it finally goes to this the denominator over here becomes smaller, it becomes larger, and this goes to e to the power of 0, which tends towards 1, and therefore this denominator becomes larger as t goes to infinity. Okay, and finally at t equal to infinity, this becomes equal to 1, so this is becoming n by epsilon by 2 plus 1, which is n epsilon by 3. Okay, so the energy is largest as t goes to infinity. So next we come to the problem of QD susceptibility. So if you recall that we had done a similar problem for QD susceptibility, we had derived this problem from uh, case of Fermi gases, right? When we were studying Fermi Dirac statistics, we had obtained QD susceptibility by considering fermions with given spins in a magnetic field, right? So you will see that the QD susceptibility can also be obtained from the Gibbs partition function. That is also, it can be obtained from a classical treatment as well. So how does that come about? So we consider n number of non-interacting quantized spins in a magnetic field, where the magnetic field points in the z direction at a temperature T. The work done by the field is given by Bmz, where mz is the magnetization. Basically, mz is the total magnetization, that is mu into summation I equal to 1 to n mi. For each spin, mi can take values of 2s plus 1, can only take 2s plus 1 number of values, that is minus s to plus s in steps of integers. Okay, so for this system, we have to first find the Gibbs partition function. So what is the partition function over here? Partition function is basically exponential of minus beta h. And what is h? H is basically given by minus of b dot m, where b minus b dot m is the magnetic energy because of the field. The work done by the field is given by bmz. Therefore, the Hamiltonian is equal to minus bmz. That is, the work done on the field is equal to minus bmz. Therefore, the partition function is equal to e to the power of minus beta into Hamiltonian, which is equal to exponential of beta into bmz. So what is mz? Mz is given by this expression. Therefore, it is equal to summation over all microstates exponential of beta b into mu summation I equal to 1 to n mi. Okay, and then since there are n number of identical spins over here, therefore this becomes a product over n number of summations equal, and then this removes the constant on mi, and this can be written as a summation over mi from minus s to plus s e to the power of beta mu b into mi with the product over n number of such summations. Therefore, now you see that this is an expression that is the sum of a finite GP series whose first term is equal to e to the power of minus beta mu bs, and the last term is equal to e to the power of beta mu bs, and the common ratio is equal to e to the power of beta mu b. Okay, if you evaluate this finite GPCD sum, then what you get is this expression for the partition function over here. And if you use the trigonometric identity for sine hyperbolic, so sine hyperbolic is equal to e to the power x minus e to the power minus x divided by 2. If I use the sine hyperbolic identity, then I obtain that z is equal to sine hyperbolic beta mu b s plus 1 by 2 s plus half divided by sine hyperbolic beta mu b by 2 whole raised to the power of n. All right. So there is a misprint over here. This will be a plus, this will be a minus, this will be a plus, this will be a minus. Okay. So once we do that, we have obtained the classical partition function, Gibbs partition function. Now from that, we have to calculate the Gibbs free energy and show that for small b, the Gibbs free energy has this particular form. So the Gibbs free energy is given by E minus Bm, which is equal to minus kBT log Z. So I have Z over here. So minus kBT log Z becomes equal to minus n kBT into log of this quantity. So now I use the expression for of sine hyperbolic theta for small theta. Why? Because I am given that I have to calculate g for small b. So if I take b to be a small quantity, then the argument of the sine hyperbolic becomes small. So therefore, sine hyperbolic theta for small theta can be written by Taylor expanding these exponentials as half into 2 theta plus 2 theta cubed by 3 factorial plus order theta to the power 5 terms. So if I set alpha equal to beta mu b, then I obtain that g is equal to this thing. Okay. And if I further simplify the expression and use the Taylor expansion of the logarithm of 1 plus x, then I am able to arrive at this form of the Gibbs partition function of the Gibbs free energy in the limit of small b. Now I have to calculate the zero field susceptibility, that is chi equal to del mz del b at p equal to 0, and so that it satisfies the Curie law. So the magnetic susceptibility chi equal to del m del b is obtained by noting that the average magnetization is equal to kbt del lnz by del b, which is equal to minus del g by del b. Therefore, chi is equal to del b of average mz, which is equal to minus del b of del g by del b. Now, since I'm finding the zero field susceptibility, I can take this form of the Gibbs free energy, which I had calculated in the limit of b going to 0. And from this, if I take the second derivative of this, I obtain chi is equal to n mu squared ts into s plus 1 by 3 kbt. So this obeys the Curie's law, that is chi is inverse proportional to t, with the constant of proportionality c being equal to n mu square s into s plus 1 by 3 kb. Right. So any questions up till now or any doubt?
No, sir.
Okay. So then moving on to the second last question which I have for today. Molecular oxygen. So molecular, this is similar to the previous question only we saw. This also has a magnetic field and spins. So molecular oxygen has a net spin magnetic spin of s of unity. So if the total spin is unity, that means the spin is quantized to three values of -1, 0, or +1. And the Hamiltonian for an ideal gas of n such molecules in a magnetic field which points in the z direction is given by summation I pi square by 2m minus mu b szy. Because the magnetic field is in the z direction, the spins also point in the z direction. So you see that szy can take three values, -1, 0, and +1. So treating the momentum and position coordinates pi and qi classically, but the spin degree of freedoms as quantized, we have to find the partition function. So partition function is basically again an integral over the position and the momentum coordinates, right? So basically the summation over mu s over e to the power of minus beta into this quantity. So first, I can easily take the momentum coordinates outside because this is independent of the spin coordinates. If I do that, then the integral I get n number of Gaussian integrals from the momentum coordinates, which evaluates to 1 by lambda to the power of 3n, right? I have a factor of 1 by n factorial, which comes from the indistinguishability. Then I have the position integral over the n number of position coordinates, which gives me a factor of v to the power n. And then there are the n number of spins, and I can which gives me basically a summation over m going from -1 to +1 e to the power of minus mu beta m, and there are n number of such summations, product of n number of such summations. If I do that, I get this term e to the power of beta mu b plus 1 e to the power minus beta mu b whole to the power n, and combining all these things, I get the partition function. Okay, so what are the probabilities of for a set of a specific molecule to take values of -1, 0, and +1 at a given temperature T? So probability of a set taking a value of -1 is basically given by the expectation of e to the power of minus beta mu b, and the expectation, as you know, is taken over the various momentum and position coordinates. And if I do that and I divide by the total probability, then the integrals over the position and the momentum coordinates will themselves cancel out because they give the same factors. And in the numerator, I will have this factor of e to the power beta mu b. And in the denominator, I'll be left with this factor, which is e to the power beta mu b plus 1 plus e to the power minus beta mu b. Now you'll see e to the power beta mu b plus e to the power minus beta mu b is equal to 2 cos hyperbolic of beta mu b. So that is what this is, and there is plus 1 over here. Therefore, the probability of Zi of a given molecule to take value of -1 is given by this quantity. If it is 0, it is 1 by this quantity, and if it is plus 1, then the probability is this. Now, what is the average magnetic dipole moment? Expectation m by v, where m is given by summation of this. So in the previous question only, you saw that the average dipole moment was given by kbt del nz by del v. Here also it's the same thing. It is 1 by beta, which is beta is 1 by kbt del lnz by del b. And z is given by this expression. If I take a derivative with respect to b, I get n mu 2 sine hyperbolic beta mu b by 2 cos hyperbolic beta mu b plus 1. And similarly, I can calculate the zero field susceptibility also, which is del expectation m by del b. So I take a derivative of this thing with respect to b, and this is equal to 2 by 3 n beta mu square. So again, here also the Curie's law is verified because beta is 1 by kbt. So again, here chi goes as 1 by kbt. Okay. So this also verifies Curie's law. And this in fact follows from this expression over here if I put s equal to 1. Okay, if you put x equal to 1 over here, then the constant of proportionality is equal to 2 by 3 n mu square by kbt. Here also same thing, 2 by 3 n mu square by kbt. Okay, so here's the last problem of today, that is polar rods. So consider rod-shaped molecules with moment of inertia I and a dipole moment mu. The contribution of the rotational degrees of freedom to the Hamiltonian is given by this thing. So the Hamiltonian for this, so basically rod-shaped molecules have moment of inertia I and a dipole moment mu, and they can rotate about their axes, which gives rise to a spin dipole moment. Okay, they can rotate about their axes, and therefore the contribution from the rotation comes from this Hamiltonian over here, which is given by 1 by 2 p theta square plus p phi square by sine square theta minus mu e cos theta, where E is the external electric field. Okay, the external electric field gives rise to a dipole moment, electric dipole moment of mu. So from this, I have to calculate the contribution of the rotational degrees of freedom of each dipole to the classical partition function. So what is that? The classical partition function is obtained by integrating over the angles theta and phi. Okay. And here I'm said that I have to calculate for each dipole. So here n is equal to 1. Therefore, the contribution to the partition function from the rotational degrees of freedom, basically the degrees of angles theta and phi, is given by 1 by h square, because there are only 2 degrees of freedom, that's why h square, integral over d theta and d phi. then integral over p theta and p phi e to the power of the Hamiltonian minus beta into Hamiltonian, right? So I can, what we do is that we have a Gaussian integral over p theta square and a Gaussian integral over p phi square. We first do the Gaussian integrals over p theta square and p phi square and the azimuthal integral over phi, and then we finally get an integral over theta. And while doing the integral over theta, we substitute x equal to cos theta. If we do that, then we get z rotational to be equal to this thing. And we can easily evaluate the integral from -1 to +1 by doing integration by parts. And then we obtain z is equal to 8 pi square I by beta h cross square sine hyperbolic beta mu e by beta mu e. So from the partition function, I can calculate the mean polarization of each dipole, which is equal to del. If you look at this expression for the Hamiltonian, you have mu cos theta over here. So you can calculate that from the partition function by taking a derivative with respect to beta e. That is del of ln z rotational by del beta e gives me the expectation of mu cos theta. And therefore this turns out to be equal to mu into cot hyperbolic beta mu e minus 1 by beta mu e. Then the zero field polarizability is given by del P by del E. Just like we had zero field susceptibility for magnetic spins, here we have polarizability for a dielectric, for polar rods basically. Therefore, chi t is equal to del P by del E. If I take del E of this expression, I get 1 mu square by 3 kBt. Here also we see that the zero field polarizability falls off as 1 by t for E equal to 0. Now calculate the rotational energy per particle and comment on its high and low temperature limits. So the rotational energy per particle, the mean rotational energy per particle is given by mean of rotational energy, which is equal to minus del beta of log of partition function, which is equal to 2 kBt minus mu e cot hyperbolic beta mu e. So in the high temperature limit, you will see that this gives me basically beta, this gives me 1 by beta mu e. In the limit of x going to infinity, cot hyperbolic is basically gives me 1 by x. Therefore, this is of the, so this becomes equal to mu e into 1 by beta mu e, which is 2 kBt minus kBt, which is equal to kBt. Okay, and at low temperatures, what happens is that this quantity is equal to 1. Therefore, I have minus mu e plus 2 kBt, and the polarization is saturated. So as k goes to 0, it saturates at minus mu e. And how does the rotational heat capacity of the dipole look like? So if I take a del T of this expression, I get the rotational heat capacity of the dipole. So at low temperatures, this is equal to basically 2 kb if I do a del T of this expression. And at the high temperature, it decreases to 1 kb and it saturates. And while there is a Ni at kBt equal to mu e. So basically it first increases and then decreases to kb at high temperatures from 2 kb at low temperatures. Okay, so that is all I had today. So I'll stop sharing my screen now. Yes. So are there any doubts or questions from today's session? Yeah, any doubts or questions or anything which you would want to cover more?
No doubt, sir.
Okay. So if there are no doubts, then we will meet again next day, same time, same place. Okay. So I'll
Okay,
close
sir.
the meeting for today.
Thank you, sir.
Okay. Bye.
Bye, sir.